Hello everyone, welcome to the course of Software Defined Networking. In this lecture, I'm going to talk about quality of service in SDN. The objective for today's lecture is that at the end of this lecture, you would be able to understand some basic concepts related to the TCP IP module, specifically to the TCP layer. You would also be able to describe the quality of service architectural framework and also summarize some key concepts of the integrated services architecture and differentiated services architecture. In addition to that, you would be able to understand the concept of SLA, service level agreements. And finally, you would be able to present an overview of the Openflow quality of service support. In this regard, the main contents for this lecture are: we will start with a background, some concepts related with the TCP like sliding window, like sequence number response, acknowledgement, and other concepts. After that, we will study quality of service architecture framework and then the two different types of services, the integrated services and the differentiated services. After that, we will learn about service level agreements, and finally, we will finish this lecture with the Openflow quality of service support. So let's start with the background. Well, historically or traditionally, the internet and other IP-based network, they try to provide best effort delivery service. What does it mean? The best effort. Actually, this means that the network will attempt to allocate the resources with equal availability and priority to all the traffic flows. There is going to be no priorities for any specific application, for any specific traffic pattern, or for any type of load. And they will not handle the customer requirements. This is what happened historically in the internet and in the IP-based networks. Now, in such type of network, in order to protect the network from congestion and to guarantee that some flows do not crowd out other flows, some congestion control mechanism were introduced. And one of the most important congestion control technique that was introduced earlier but still is widely used is the TCP congestion control mechanism. For each TCP connection between two end system or between two end devices across a network, we need to understand some concepts. The first concept is related to the sliding window. It's actually a buffer, and that buffer is represented as a set of slices, as you can see here. And these slices are known as sliding window that occupies part of the circle at any time. At the sender side, when the senders send a packet, the corresponding slide is marked. Here you can see we have used the blue color to represent the marked slice. When all slices are marked, it means that the buffer is full. When the buffer is full, no further messages can be accepted from the application layer. However, when an acknowledgement arrives, the corresponding slide is unmarked, which means the packet has successfully arrived at the destination. If some consecutive slices from the beginning of the windows are unmarked, the window slides over the range of the corresponding sequence number to allow more free slices at the end of the window. And one of the sliding window concept has been shown in this figure. This is the sliding window at the sender side. However, it is important to remember that this diagram actually represents an abstraction. The actual situation uses computer variables to hold such stuff and to deal with the sliding window concept. In this particular case, for example, let's consider the diagram at A. Here, starting from 0, the sender has sent out 4 packets. However, their acknowledgements are not received yet. So this is the sequence number of the first packets being sent out, and this is the sequence number of the next packet that would be sent out by the sender. After some time, another packet has been sent out, and now the next sequence pointer is now pointing to the slice number 5. After some time, you can see that now 7 packets have been sent out, 0 to 6. And finally, in D, you can see that now the sender has received an acknowledgement for the slice 0. So now he is expecting the acknowledgement for the next outstanding packet, and the pointer is now pointing to location number 1. Okay. So this is the basic concept of sliding window. Actually, there is a lot more about the TCP, about the sliding window, but we will try to avoid the details. Our next concept related to the TCP is about a protocol which is known as stop and wait protocol. However, before going into the details of this protocol, let me tell you that beside from sliding window, we also have sequence numbers and acknowledgement at the TCP layer. And mostly they are used for error control mechanism at the transport layer. Okay, so the sequence numbers are actually used to number the packets. When a packet is corrupted or lost due to any reason, the receiving transport layer can somehow inform the sender to resend that packet by using the sequence number. Hey, I have received packet number 1, packet number 2, packet number 3, but packet number 4 is missing. Could you please send me again packet number 4? So the receiving transport layer can also inform the sender about the lost packet, or even it can inform the sender about the duplicate packet if it received a packet more than 1, or if it received packet that have the same sequence number, or maybe sometimes some packets are arrived out of order. It could be due to the sequence number, the receiver would be able to recognize those packets as well. So sequence number and acknowledgement, they actually play a very important role in the TCP at the TCP layer. The receiver side, actually sequence number are generated by the sender, while the acknowledgement are generated by the receiver. The receiver side can send an acknowledgement for each of the packet that has arrived safe and sound. Okay, now based on these concepts, various algorithms are used by the sender and receiver. And the basic concept of the TCP is to reduce the congestion on the network. And for that purpose, there are different protocols available. For example, one of the protocol is known as simple protocol, another protocol is stop and wait, another one is go big N protocol. Similarly, we have selective repeat protocol and bidirectional piggyback protocol, and many other protocols are available. So we are going just to briefly discuss the stop and wait protocol. Actually, at the TCP layer, we can divide the protocols into 2 layers, connection oriented or connectionless. So stop and wait protocol is actually a connection oriented protocol which follow the 3-way handshake. before exchange of any information, they have to establish a connection. And this protocol use both flow control mechanism and error control mechanism. This is a simple protocol. So the sliding window of stop and wait protocol is 1. The sender sends one packet at a time and wait for an acknowledgement before sending the next one. Okay, so you can see at the sender side, we have like on top we have the application layer, and then we have the transport layer. So we are studying the transport layer here, the TCP. At the transport layer, you can see application send out a packet, some data to be sent out toward the receiver, and then the transport layer attach some heading and also some control information. You can see here what is data information, sequence number to uniquely identify this packet, checksum for error purposes. So flow control with the help of sequence and error control with the help of checksum. And then it sent out the packet toward the receiver. At the transport layer, at the receiver side, the transport layer will receive the packet and will hand over it to the application layer. Okay. After receiving successfully reception of the packet, the receiver will send an acknowledgement. And here is the acknowledgement packet. Actually, it has two fields: acknowledgement number of the packet that it received, and a checksum for error correction or maybe for error detection. So this is a simple protocol. The sender sends one packet at a time and wait for an acknowledgement. To detect a corrupted packet, we need to add this checksum to each packet. When a packet arrives at the receiver side, it is checked. If the checksum is incorrect, the packet is discarded because it is an indication that the packet has been corrupted. Now, the silence of the receiver is actually a signal for the sender that the packet was either corrupted or lost. So every time the sender sends a packet, this is another concept, it will start a timer. Now, if the sender receives an acknowledgement before this timer expires, the timer is stopped and the sender sends the next packet. So if an acknowledgement arrives before this timer expires, the timer is stopped and the sender sends the next packet. But if the time expires and the sender does not receive any acknowledgement, then the sender will resend the previous packet because it will assume that the packet was either lost or it was being corrupted. This means that the sender needs to keep a copy of the packet until its acknowledgement has been arrived. To further explore the concept of stop and wait protocol, we have an example here. I will not spend too much time on this slide, but the concept is simple. Let me briefly give you an overview. We have a sender, we have a receiver. This is the sliding window. As I just told you that it uses a sliding window of size 1, so you can see here 0 and 1. So it sends out a packet 0 and it will wait for an acknowledgement. Once it sends out the packet, it will start the timer. And then after receiving the packet, the receiver will send acknowledgement. Actually, it will send acknowledgement for the next packet it is expecting. Okay, like, hey, 1, it indicates that I have received the packet 0. Could you please send me another packet? So it will send packet number 1. Now suppose the packet has been lost. The timer is there. The timer is expired, timeout, but the sender does not receive any acknowledgement. So what happens? It will resend the same packet again. The packet arrives successfully. It will ask for the next packet, and then it will send out the next packet. You see the sliding window is increasing on the other side as well. It will send out the packet. Now here the packet is received, but the acknowledgement has lost. Now this is a problem with this protocol. The timeout, it does not receive the acknowledgement. So what will happen? The sender will resend the same packet again, although it was successfully received by the receiver. However, it is a duplicate packet. So the duplicate packet are discarded by the receiver in the stop and wait protocol. So why it is called stop and wait protocol? Because the sender send out a packet and then it stop and wait for a response or for an acknowledgement. Okay, after studying briefly the TCP basic concepts, let us study another concept which is related with the quality of service. Before going into the detail of this architecture framework, let us see what is actually quality of service. What does it mean? We talked about quality of service at the beginning of this course, but let me give you a very short example and a brief definition of the quality of service again. So actually, quality of service is the measurable end-to-end performance properties of a network service. Service could be anything. That service could be guaranteed in advance by using SLA, service level agreement. And this agreement is between two parties, the user and the service provider. So you can say that quality of service is actually the collective effect of service performance, which determines the degree of satisfaction of a user of the service. You are offering a service to a user, and then up to what degree your user is satisfied with that service. So it is about supporting the characteristics and properties of specific application. However, different applications may have different requirements and different needs. For example, telemedicine applications. They want high level of accuracy. Accuracy is more important than delay, or you can say than jitter. While, for example, for IP telephony, for audio conferencing, the jitter and delay are the key requirement which must be minimized. So different applications have different requirements and different users are interested in different applications. So we need different types of matrices, different types of parameters for each and every service that we offer to the customer. On the other side, quality of service is something else. It is actually the measure of performance as reported by the user, which means how the user see your end product. And we talked about quality of experience at the beginning of this course. So actually it is about the human opinion, their psychology, their ease of use of the service that you are offering to them. Now let's come toward the architecture. This architecture that we are going to see in a moment was developed by Telecommunications Standardization Sector, ITU, at the ITU, and it is known as Y.1291. It is actually something from the Y series, but we will not go into the details of the Y series. But it is an architecture for us. It is important that to know is that it was developed by the ITUT. Okay, so this figure actually shows the architecture and it also shows the different elements of the architecture, and you can see we can organize them into three different planes. And you're quite familiar with these planes. One thing is different. We do not have the application plane here, rather we have the management plane. So we have the data plane, we have the control plane, and we have the management plane. First, let us see what is the data plane. Actually, the data plane includes such type of mechanism that operate directly on the flows of the data. Remember, data plane of the SDN, where the actual data flows happen. So it contains mechanism dealing with the traffic directly. And these mechanisms include different elements. For example, you can see we have the buffer management, we have the congestion avoidance mechanism, we have the packet marking, we have the queuing and scheduling stuff, we have the traffic classification and traffic shaping and traffic policing stuff. Policing is policing. Okay. So first let us see these individual elements one by one. Traffic classification, as the name indicates, refers to the assignment of the packet to a traffic class. We have different classes of traffic and you received a packet. So now it's the responsibility of the traffic classifier to assign that packet to a specific class. And actually this thing is done by the ingress router at the edge of the network. An ingress router is a concept which is mostly related with the MPLS network, but it is installed at the edge of the network. Okay, so typically the classification entity looks at different fields of a packet. You know a packet is composed of different fields. So this classification entity will have to look at different fields in order to decide to assign the packet to a specific class. For example, what is the source address? What is the destination address? What is the application payload? What is the quality of service marking that we will study in a moment? And other things to determine to which flow the packet will belong to, or to which class the packet will belong. This classification actually provides network elements a method to measure the relative importance of one packet over another, something related with the quality. If you are assigning a packet to a specific class, it means one packet is important over another class or over another packet. And then we have the packet marking. Actually, it is responsible for two functions. First, packet may be marked by the ingress node, the node at the edge of the network, to indicate some form of quality of service that the packet should receive. And an example of this marking is differentiated service, which we will study in a moment. Actually, the IP version 4 and IP version 6 packet, they have different fields. And one of the field in them is the diffserv field. So this packet marking will inspect specific field of the IP version 4 and IP version 6 packets in order to determine the traffic class. Secondly, the packet marking can be used to mark packets as non-conformant. What does it mean? It means that either the node at the edge of the network or even the nodes which are inside the network, like the intermediates node, they may drop any packet if congestion is experienced in the network. Okay, so that is the second reason. Then we also have the traffic shaping, and shaping actually controls the rate and volume of the traffic that is entering into the network on per flow basis. The entity responsible for traffic shaping will actually buffer the non-conformant packets. Okay, the packets that are going to be dropped. Up to which extent it will buffer the non-conformant packets until it brings the respective aggregate in compliance with the traffic limitation for this flow. So the resulting traffic is smooth, not bursty, as the original, and is more predictable. What does it mean? Simply, it means that based on the current condition of the network, it will decide to buffer the packet for some time, and it will keep eyes on the original traffic. If the congestion, chances are there, it will hold the packets. Okay, otherwise it will let them go. And then we have the congestion avoidance, which is also related with the network load. Congestion avoidance deal with means, with mechanism for keeping the load of the network under its capacity, such that it can operate at an acceptable performance level. So the specific objectives are to avoid significant queuing delays and also to avoid congestion collapse. And you know how we can avoid actually congestion? Actually, unless there is an explicit indication, packet loss or timer, as we just saw in the TCP mechanism, the timer expiration is normally an indication of the network congestion. Okay, so if you are not receiving acknowledgement and your timers are getting expired again and again, so this is an indication that there is a load on the network. So you need a mechanism to control that load. And TCP have several mechanisms for handling the load on the network. And then we have the policy stuff here, which is related with the traffic, and it actually determines whether the traffic being presented is on a hop by hop basis or not, whether the traffic is following the policies or not. The non-conformant packets may be dropped, may be delayed, or other packets sometimes they may be labeled as non-conformant as well. Then we have the queuing and scheduling stuff algorithms, and this is simple. They are also known as queuing discipline algorithm. They actually determine which packet to send next. Okay. And then we have the buffer, the queue management, which is also known as the buffer management stuff. And it actually manage the length of packet queues, something related with the capacity of the queues. And it actually drop packets also when necessary or when it is appropriate. So active management of queue is concerned primarily with congestion avoidance. We know that at the early days of the internet, the queue management discipline was to drop any incoming packet when the queue was full and there was no space available. However, there are certain drawbacks to this simple method of dropping the incoming packets if the queue is full. What are those disadvantages? The first disadvantage is that there is no reaction to congestion until it is necessary to drop the packets. Whereas a more aggressive congestion avoidance technique would likely to improve the overall network performance. And another drawback of this technique is that queues tend to be close to full, which cause an increase in packet delay through a network, and which can result in a large batch of drop packets for bursty traffic. And this will lead to unnecessary retransmission of the packets. But now more sophisticated queue or buffer management algorithms are available in the literature. Now coming toward the control plane, the control plane is concerned with creating and managing the pathways through which user data flows. And it includes like the admission control, resource reservation, and quality of service routing. So first let us see what is the role of admission control element. What user traffic should enter into the network is like an officer standing at the gate, allowing and disallowing people to enter into the building. It may be in part determined by the quality of service requirements of a data flow compared to the current resource commitment within the network. But beyond balancing quality of service request with available capacity to determine whether to accept a request or not. Actually, the network managers and also the service provider, they must be able to monitor, to control, and to enforce use of network resources and services based on different policies. Okay, so for that purpose, we need admission control mechanism. And then we have the resource reservation. And the resource reservation is a mechanism that reserves the network resources, as the name indicate, resource reservation. And the resources are reserved on demand, and they are reserved for delivering desired network performance. Okay, for example, you want to give a party to your friends. So in order to avoid congestion and other problems, you reserve a restaurant in advance, or you reserve some tables in advance. In the world of networking, there is a protocol for this purpose, and that protocol is known as RSVP protocol, which stands for Resource Reservation Protocol. Okay, so what is resource reservation protocol? It is actually a transport layer protocol that is specifically designed for resource reservation across a network, and it can operate over IP version 4 and IP version 6 as well. It is actually a mean by which applications communicate their requirements to the network, like the people communicate their requirements to the restaurant's owners in an efficient and robust manner. And it is actually developed to support traffic requiring a guaranteed quality of service. That was the purpose for the development of the RSVP protocol. And then the third component is quality of service routing. Quality of service routing concerns the selection of a path satisfying the quality of service requirement of a flow. So quality of service routing actually determines a network path that is likely to accommodate the requested quality of service of a flow. The path that is selected is most likely be depending on quality of service metrics. Normally what happens in traditional routing protocols, the least cost path through the network is selected for routing. But for quality of service, we have to consider other metrics as well. For example, what is going to be the quality of the service if the load increases, okay, and other stuff as well. Then we have the third module, which is the management plane. And actually this plane contains mechanism that affect both the control plane and the data plane mechanism. It deals with the operation, with the administration, and with the management aspect of the whole network. And it includes something very important that is known as SLA. What is SLA? SLA typically represents the agreement between a customer and a provider of a service that specify the level of availability, serviceability, performance, operation, and other attributes of the service. And then we have the traffic metering and recording. Traffic metering and recording concerns monitoring the dynamic properties of a traffic stream using performance metrics like data rate, like packet loss rate, like jitter, etc. It involves observing the traffic characteristic at a given network point, and it also collect and store the traffic information for analysis and further actions. We do have the traffic restoration, And traffic restoration actually refers to the network response to failures. And a number of protocols layer and techniques are involved for in this traffic restoration process. And finally, the policy. Well, policy is actually a category that refers to the set of rules defined for administration, for management, and for controlling access to the network resources. And policies are actually rules which typically are used for controlling access to different resources of the network, for management of the resources, and for administration of the resources. They can be specific to the need of a specific service provider, or maybe it could be for the whole network services as well. So it depends on the type of the policies. Okay, so this is about the quality of service architecture framework. And now let's move to integrated service architecture. Before going into the details of the integrated service architecture, let me give you a background. Historically, the internet has following the best effort delivery model. There is no admission control, and the network offer no guarantee about the delivery of the packets. Most of the application on the internet were elastic in nature, as we saw at the beginning of this course, elasticity. In that way, they tolerated packet delays and packet losses, and hence they could be served by the best effort model. But this was the historical aspect of the internet. There are new applications today on the internet that do not necessarily follow the best effort model. And these new applications like voice application, like videos application, conferencing, real-time applications, they are very different from the traditional data applications. Now, these emerging multimedia applications have very different characteristics and different requirements than the traditional data applications. Now, these new real-time applications, they are typically less elastic and less tolerant to delay variation. So we can say that these applications do not perform well under extreme variations in the delay. So if we were to have, for example, a highly congested link, it would be difficult to have a good quality voice or video application running on it. Besides, these applications do not adapt to congestion, and this leaves the adaptive data applications with less bandwidth. Now, what I want to say is that the current internet model, the real-time applications do not perform adequately and do not interface well with the data applications. And hence it is necessary to extend the internet model in order to support the new era of applications. Now, in order to meet the objectives that I just mentioned, the integrated services architecture model was proposed. And it was proposed by the IETF. Actually, they developed a suite of standards under the general umbrella which is known as Integrated Services Architecture, or ISA in short. Generally speaking, there are 4 standardized approaches. The first one is the integrated services. The second one is the diff services, and these two that we are going to cover in this lecture. But we also have the MPLS model, and we also have another IP Cablecom dynamic quality of service model available as well. But in this lecture, we are going to focusing on the ISA and also on the diff services model. So ISA intended to provide quality of service transport over IP based networks. And it is defined in the RFC, and the RFC number is 1633. Although this ISA is not implemented in many products. However, the architecture principles are in wide use. So the central design issue for this ISA is how to share the available capacity in times of congestion. For IP-based internet that provides only a best effort service. So the tools for controlling congestion and providing services, they are limited. So what we need, the routers have uh, to to follow two mechanisms to work with this ISA, and those are routing algorithms and packet discard, and these are simple. Some routing protocols in use in internets allow routers to be they allow the routes to be selected to minimize the delay. How it is possible? We know that router exchange information to get a picture of the delay throughout the internet. So minimum delay routing helps to balance loads and decreasing the local congestion, and also help to reduce the delay seen by the individual TCP connections. And we also have the packet discard. As the name indicates, when a router buffers overflow, it discards the packets. And typically, which packet is discarded? The most recent packet it received is discarded. And the effect of packet lost on a TCP connection is that the sending TCP entity, as we know, will have to resend the packet. Now, these two tools, they work reasonably well. However, these techniques are inadequate for a variety of traffic that are coming in the internet these days. So in the ISA, actually we have to make use of different functions to manage the congestion and provide quality of service. What are those functions? The first function is admission control. For quality of service transport, other than the best effort transport, the ISA required that a reservation be made for a new flow. You need to reserve the resources for a new flow. If the routers collectively determine that there are insufficient resources to guarantee the requested quality of service, the flow is not admitted. A simple example, if a restaurant is not able to provide you the space, they will explicitly tell you that the services that you are requesting, we are not able to offer you. So the admission is not admittable. The flow is not admittable. And the protocol used for such thing is again RSVP, Resource Reservation Protocol. Then we have the second function which is related with the routing. And for that we have to use the routing algorithm. The decisions may be based on a variety of quality of service parameter. Normally, traditionally, we give focus only to delay. But here in this case, there could be other parameters as well. And then we need the queuing discipline, and it play a vital role in the ISA. It is important for effective queuing policy that will take into the account different requirements of different flows. And finally, the discard policy is like the function, the packet discard. What it do? The discard policy determines which packets to be dropped when a buffer is full and when new packets are arrived. So this policy can be an important element in managing congestion and also in meeting the quality of service guaranteed. Now some components of this ISA. This figure shows a general depiction of the implementation architecture for the ISA, and this is implemented within a router. You can see a line here, this line. Below this line are the forwarding functions of the router. These are executed for each packet. and therefore must be highly optimized. While the remaining function above this line are the background functions that create data structures and that are used for forwarding functions. So this lower portion of the figure actually corresponds roughly to the data plane, and this upper portion roughly corresponds to the control plane. Now let us see these different elements. First, the background, reservation protocol. This element. Actually, this is a protocol which will reserve resources as we just saw in the function. So it will reserve resources for a new flow at a given level of quality of service. Remember, we are talking about the quality of service. So for providing quality of service, you need to reserve the resources. And it is used among routers and between routers and the end system as well. The reservation protocol, again, that is responsible for maintaining flow specific state information is the RSVP that is used for this purpose. And this protocol actually updates the traffic control database that is used by the packet scheduler to determine the service provided for packets of each flow. And then we have the admission control. When a new flow is requested, the reservation protocol invokes the admission control functions. Remember, these concepts seems like the same things. Admission control we studied in the previous slide as well. So this module actually determines if sufficient resources are available for this flow at the requested quality of service or not. And this determination is based on the current level of the commitment to other reservations or on the current load on the network. So different factors can affect this decision. Then we have the management agent, and this is actually a network management agent, and it can modify the traffic control database. You can see it has access to the traffic control database, so it can modify it. And it also directs the admission control module to set admission control policies. And then we have the routing protocol is actually responsible for maintaining a routing database that gives the next hop to be taken. It's like the routing tables for each destination address and each flow. Now these background functions, they actually support the main task of the router, and which is the forwarding of the packets. The two principal functions areas that accomplish forwarding are classifier and route selection and the packet scheduler. For the purposes of forwarding and traffic control, incoming packet must be mapped into classes. Remember the concept of classes? So a class may correspond to a single flow, or it could correspond to a set of flows with the same quality of service requirements. For example, the packets of all videos flows or the packet of all flows attributable to a particular organization may be treated identically, and it will create a flow. And this is important for resource allocation and also for queuing discipline. Now the selection of a class is based on the field. Remember the field in the IP version 4 and IP version 6 adder? So based on the packet class and its destination address and other things, it decides which flow will take which class. And then finally we have the scheduler, and it is actually the function which manages one or more queues for each output port. It determines the order in which queue packets are transmitted and the selection of packets for discard as well, if it is necessary to discard the packets. And decisions are made based on packet class, the contents of the traffic control database, and the current and past activity of the outgoing port and things like that. Next, we have some services related with the ISA architecture. Actually, the ISA service flow of packets, and that is defined in two levels. Like a number of general categories of services are provided, each of which provide a certain general type of service guaranteed. And second, each category, the service for a particular flow is specified by the values of certain parameter as we just discussed. Actually, there are three categories of services and they are defined in the architecture, and they are guaranteed service, controlled load, and best effort. First, the guaranteed service. Actually, it is a class that provides FIM, end-to-end delay guaranteed. This service guaranteed both delay and the bandwidth. The network in this case will compute various parameters describing how it will handle the flow, and by combining the parameters, it is possible to compute the maximum delay a packet will experience. Now, the delay normally has two parts, a fixed delay and a queuing delay. Fixed delay is a function of the chosen path, and it comprises of transmission delay, etc., and is determined by the setup mechanism. But the queuing delay is actually determined by the guaranteed service. It is actually a function of two parameters. We will not go into the details of that because it involves explanation of other terminologies like the token buckets and things like that. But the data rate of the application that requesting the service is important. So this service is intended for applications which need a FIM guarantee that a datagram will arrive no later than a certain delay bound. Like you have to give a guarantee to your user, hey, we give you surety that whatever the reason is, your packet will arrive in this much time to the destination. A very simple example. So the guaranteed delay or this service bound a FIM1. The delay has to be set large enough to cover extremely rare causes of long queuing delay. Normally, you apply for a service and the service provider send you an email. We will resolve your issue within 48 hours. And then you see your query is resolved within 5 minutes. They actually tell you the maximum delay in order to be on the safe side. So same is the case with guaranteed services. Okay, since the guaranteed delay bound is a FIM1, so you have to be careful while giving this guaranteed services, because it assured that the service will be delivered within the specified time mentioned. So you have to specify an upper bound. That is important to remember on the queuing delay through the network. And for that, you have to keep in mind different types of delay. Like we have the propagation delay, we have the queuing delay, we have the transmission delay, and things like that. Also, we have other type of latencies and things like that. Next one is controlled load. Controlled load service in an enhanced quality of service, and it is intended to support applications requiring better performance. Better performance than what? Better performance than the performance that was provided by the traditional best effort services. It approximates the end-to-end behavior provided to best effort service under unloaded condition. Well, the assumption here is that under unloaded condition, a very high percentage of the transmitted packets are successfully delivered to the end nodes. That is quite obvious. And the transmission delay experienced by a very high percentage of the delivered packet will not vary much from the minimum transmission delay. Now, the control load service is particularly aimed at supporting the predictive or the delay adaptive real-time class. The network ensures that adequate bandwidth and packet processing resources are available to handle the requested level of traffic. So the service tightly approximate the behavior visible to application receiving best effort services under unloaded conditions. We also have the best effort, and the best effort is the traditional way. But in the current model, the current ISA architecture model, it is followed in the which is followed in the internet is the best effort model. And most data application are most suited to operating in this way, best effort. The application like traditional application like telnet, like FTP, etc., they do not have any hard deadlines in terms of delay. So they wait for data and process it as soon as they receive it. This service class will continue to be supported in addition to the real-time classes like the guaranteed and controlled load services. Okay, there is a related concept which is known as queuing discipline. And this important component of the ISA implementation is related with the routers. And the simplest approach then can be used by a router is very famous one, that is first in first out queuing discipline at the each output port. A single queue is maintained at each output port of the router. When a packet arrives and it is routed to an output port, it is placed at the end of the queue. As long as the queue is not empty, the router transmits packets from the queue, taking the oldest remaining packet next. However, there are several drawbacks of this approach. For example, no special treatment is given to the packets from flow that are of high priority or they are more delay sensitive. There is no special treatment. Similarly, if a packet of smaller length, a number of smaller length packets are queued behind a long packet, FIFO queue mechanism will result a large average delay per packet. The shorter packets were, if you are not using the FIFO, then you can transmit the shorter packet before the longer one in order to get better quality of services. And also a selfish TCP connection which ignore the TCP congestion control rules can crowd out confirming connections. If congestion occurs and one TCP connection fails to bake off, other connections along the same path segment must bake off more than they would otherwise have to do. Now, to overcome these problems of the FIFO, a number of more complex routing algorithms have been implemented in the routers. For example, priority queuing algorithms. And for this, each packet is assigned a priority level, and there is one queue for each priority level. For example, in the Cisco implementation, 4 different levels are used, like the high priority, the medium priority, the normal priority, and the low priority. And then we have the custom queuing policies or algorithms available, which is designed to allow various applications or organizations to share the network among applications with specific minimum throughput or latency requirements. And for CQ, there are multiple queues with each having a configured setup. The queues are serviced in a round robin fashion, which is another policy, and I'm sure you must be aware of it. We also have flow-based routing mechanism available like the WFQ, weighted fair queuing. And these algorithms, the remaining 2 algorithms, they are based on a mechanism which is known as fair queuing. And with fair queuing, each incoming packet is placed in the queue for its flow. The queues are serviced in round robin fashion, taking one packet from one non-empty queue in turn. So empty queues are skipped over, and the scheme is fair in that each busy flow gets to send exactly one packet per cycle. Like you have five rows, and then you select one packet from each row in turn by using a round robin fashion. And we also have a class-based wait fair queuing mechanism which will allow a network administrator to create minimum guaranteed bandwidth class, but we will not go into the details. Okay, beside from ISA, we do have differentiated services as well. Actually, the problem with the above ISA architecture is that they required an advanced setup to establish each flow. Something that does not scale well when there are thousands or millions of flows. In addition to that, they also maintain internal per flow state in the routers and making them vulnerable to router crashes. And also, the changes required to the router code are substantial and involve complex router to router exchanges for setting up the flows. Now, for these reasons, the IETF has devised another approach that is a simpler approach to the quality of service provision. One that can be largely implemented locally in each router without advanced setup and without having the whole path involved. This approach is known as uh, differentiated services. The RFC in which the diff serve architecture is defined is 2475, although there are other RFCs available as well, but this is the main one. And it is designed to provide simpler, easy to implement, low overhead, and which will support a range of network services that are differentiated on the basis of performance. Well, there are several key characteristics of the differentiated services. For example, the IP packets are labeled for different quality of service treatment using the existing IP version 4 and IP version 6 fields. There is a field in the IP version 4 packet which is known as DS field. So it actually utilizes the DS field, which means no changes is required in the IP packet. And also the service level specification or service level agreement is established between the service provider and the user or and the customer. And this will avoid the need to incorporate diff serve mechanism in application. There are also some features like there is something which is known as traffic conditioning specification TCS, which is part of the SLS or service level specification that will specify the traffic classifier rules and any corresponding traffic profiles and meetings and marking and things like that, and traffic shaping that we studied in the previous slides. So today, diff service is the most widely used accepted quality of service mechanism that is used in the enterprise network. And there are different services that are actually provided by the diff S. And here is an example that you can see. This figure is actually focusing on the component which we just mentioned in the SLA, sorry, in the differentiated services, that is the SLS or SLA, service level agreement. So we are going to study the service level agreement. I mentioned earlier about the service level agreement, which is like a contract. And this contract is between two entities, the network providers and the customers. And this contract will define a specific aspect of the services that is to be provided to the customer. Okay. Actually, this SLA document includes several things, but the three main components are mentioned here. A description of the nature of service to be provided. What does it mean? Let me give you an example. A basic service could be like an IP-based network connectivity of the enterprise locations. It could be something like access to the internet. The service may include additional functions like, okay, if you are using our service, you would be able to do web browsing. We will also do maintenance of your domain name servers and the operation and the maintenance task, etc. So there is the description part. Then we have the expected performance level of the service. The SLA also define a number of metrics like the delay, reliability, accessibility, availability, and other thresholds that need to be defined. And this is something related with the performance, expected performance. And the third one is the monitoring and reporting, the service level. This actually describes how the performance level are measured. In point number 2, we talk about the performance levels, the metrics. So how they are going to be measured, how they are going to be monitored, how they are going to be reported. This is something which is the point number 3 focus. Let us take an example. In this case, we have a network service provider here. This network service provider maintain an IP-based network. And then we have a customer at the bottom, at the top. A customer has a number of private networks at various locations. For example, lane 1, lane 2, lane 3. Now, customer networks are connected to the provider via access routers. Router 1, router 2, and router 3. Now, the SLA dictates service and performance levels, as we just saw here, for traffic between the access routers and the provider network. However, in addition to that, the provider network links to the internet and thus provides internet access to this enterprise. This is another service. So in this case, this service provider need to explicitly told the customers about the availability. For example, hey, the network availability is guaranteed to be 100% of the time. Or another metric could be delay. What is the delay? If you want to send a packet to a node in the US, what is going to be the delay if you want to send a packet within your country, in Asia? Things like that. The latency involved, the network latency, the round trip time, the packet delivery rate, the reliability. Different metrics can be there. That could be part of this SLA. So an SLA can be defined for the overall network. In addition, the SLA can be defined for any specific service like internet access, like browsing, like FTP, etc. Finally, let us see Openflow, something related with the SDN, quality of service support. Openflow offers two tools for the implementation of quality of service in the data plane switches. These two tools are known as queue structure and meters. Queue structures, we know about it. We studied it in the previous slides. However, in the context of the Openflow, an Openflow switch provides limited quality of service support through a simple queuing mechanism. One or more queues can be associated with a port, output port. And queue supports the ability to provide minimum data rate guaranteed and maximum data rate limits. And these queue configuration take place outside the Openflow control protocol. And there is also a data structure which will define each queue. The data structures include a unique identifier and the port to which it is attached, minimum data rate guaranteed, and the maximum data rate. What is important for us in regard of the Openflow is the concept of a meter. A meter is the actual switch element, and it actually measure and control the rate of packets. With each meter, there is a set of one or more bands. You can see we have a meter table entry, and we have a band associated with it. It could be one band or it could be more than one bands depending. Now the whole story is like this. If the packet rate exceeds a predefined threshold, then the meter will trigger this band. The band may drop the packet, in which case it is known as rate limiter. Other quality of service and policy mechanism can be designed using meter bands. Each meter is defined. You can see we have a meter here. It is defined by an entry in the meter table. On top of it, we have the meter table, and this is for a switch. Now, each meter has 3 fields. It has a unique identifier, which will uniquely identify this entry. And we have a meter table, and we have counters. Now, these meters are not attached to a queue. They are not attached to a port. Rather, a meter can be invoked by an instruction, and that instruction is from a flow table entry. Inside the flow table entry, we have different fields. One of the field is instructions, and by using this instruction, you can actually invoke a meter table. And multiple flow entries can sometime point to the same meter. So a meter actually measures different things. For example, it can measure the rate of packets assigned to it, and it enables controlling the rate of those packets. So the meter measures and controls the rate of aggregate of all flows entries to which it is attached. Now multiple meters can be used in the same table, but in an exclusive way, this joint set of flow entries. So multiple meters can be used on the same set of packets by using them in successive flow tables. So this is the concept of meters. I'm not able to explain further because I'm feeling some throat issues now. So I hope you understand today's lecture. If there are some issues, we will discuss them in the live session. Thank you so much for attending the lecture. Take care and goodbye.